Let's construct a circle and a chord. Mark the middle of this chord and draw two segments through this point. We will also draw two segments through the intersection points so that the resulting construction resembles a butterfly. Then the segments XO and YO are equal, or better to say that X and Y are symmetrical about O. As you already understood, it's called the butterfly theorem. Before talking about the proof of this theorem, I would like to tell an interesting story about its discovery. It was thought that the first mention of this theorem was a publication in the journal Gentleman's Diary in 1815, and one of the solutions was written by William George Horner, a British mathematician mainly known for the Horner's method. By the way, although it was named after him, this method is much older and can be traced back many hundreds of years to Chinese and Persian mathematicians. Then it turned out that the first mention of the butterfly theorem is a bit older. In 2011, some archival records were published showing that the first who proved this theorem was William Wallace, a Scottish mathematician, astronomer and inventor known for finding the Simpson line, which was erroneously named after another mathematician, Robert Simpson. One of these archival records was a letter to William Wallace, dated 1805, from another William Herschel, who was the discoverer of Uranus and its two major moons, Titania and Oberon. In this letter, he invites Wallace to prove a geometric statement that he cannot prove himself. In response, Wallace offers him his proof, noting that this statement must also be true for other conic sections. This is where the story about three Williams ends, so let's move to the proofs. In this video, I will give, in my opinion, the simplest one, which is clear even to 8th graders. I also like this proof because it works for one of the generalizations, where instead of the midpoint of the chord, we take 2 points symmetrical to this midpoint. And so, let's get started. To begin with, we reflect the segment BA relative to the perpendicular bisector to our chord. Now consider the inscribed quadrilateral DB1A1A. Because it is inscribed, it follows that the sum of the red and green angles is 180 degrees. Also, due to the fact that A1 is parallel to our chord, angles B10X and B1A1A are equal. So the quadrilateral DB10X is also inscribed, because the sum of its opposite angles is 180 degrees. Then the angle OB1X is equal to the angle ODX, which is equal to the angle OBY. Consider the filled triangles. From the symmetry, the sides OB1 and OB are equal and the angles B10X and B10Y are also equal. We also proved the equality of the angles OB1X and OBY, so these triangles are congruent, and then the sides XO and YO are equal. The theorem has been proven. As I said, this proof will work the same way if instead of the middle of the chord we take 2 points symmetrical to it. I think that it's not necessary to simply repeat the steps already mentioned earlier, so just look at the animated picture. And so, on this I could already finish this video, but since we have already started talking about the generalizations of this problem, I need to mention a few more. Firstly, it is not necessary to draw two last segments so that the construction looks like a butterfly. We can also draw it this way. Segments XO and YO are equal. Also, as William Wallace said, the theorem works the same way and for other conic sections such as the parabola, hyperbola, and ellipse. Thank you for watching. If you want to see a video on a specific topic, then write in the comments. Goodbye.